Hello and welcome back. In this video we'll start section 2.2, which is all about shapes of graphs. And we'll first look at graphs that are increasing, decreasing, and constant on intervals. So when we look at graphs, we're going to try to read them from left to right when we're looking at increasing versus decreasing versus constant intervals. So here we can see that in this first section, this first part of this graph, our function is going up. So this is going to be an increasing interval. In the next section, we're staying about level. So this will be a constant section. So this is the next part. So this will be a constant part of the graph. Next, we'll go down, and this is decreasing for this next little interval. And then this last part, we're increasing, and you can see that even though we start out close to flat, by the end, the graph is going to be increasing by quite a lot. So you can increase at different rates, even in the same section. So a graph may not look quite as straight as some of these sections are. So we'll just have to interpret where these where the sections of this graph are going to be increasing and decreasing. You can see that as we start, we're going down until we reach this bottom point there. So we are going to be decreasing from along these values for x, and then we'd be increasing from this bottom point up to about here. So the next little section will be increasing, and then this last part is going to be decreasing. We're going down. So that's really all there is to increasing, decreasing, and constant functions. And specifically, if we want to write this down more mathematically, when we're looking at 2 points, say x1 and x2, where x1 is further to the left than x2, so x1 is less than x2, how the function varies will determine if we're increasing or decreasing or constant. If the function is getting bigger, as in f of x1, so let's say that here is x1 and here is x2, you can see that the function value at x1, we have gone up to get the function value at x2. So this is when it's increasing. Decreasing would mean when the function value at x1 is greater than the function value at x2. So we have gone down. And constant will be when things are equal. And we just want to make sure that this happens all the way inside of that all this is satisfied inside an entire interval. So we do want to break it up into sections that are increasing, decreasing, and perhaps constant. So let's look at another example here, and let's write down the actual intervals. So we can see that we start with a constant section of the graph, and we're coming in all the way from negative infinity all the way up to when x is equal to 0. This is all constant. So from 0 on down, this is all a constant graph. So the interval in which this graph is constant is going to be negative infinity to 0. There's no other constant parts of this, and we'll include 0 in this. The next part will be increasing. So let's write this down. And we can see that we're increasing from 0 all the way up to 1. But we won't include 0 because this is going to be an empty dot, and it's increasing all the way up to 1. But this isn't the only place where this graph is going to be increasing. Here, we're going to be increasing again a little bit later, starting from 2 onwards. So 2 to infinity will be increasing. Again, we will include 2, but we never include infinity. So we'll have have a parenthesis there. And since we're increasing on both sections, we want to put these together, and putting sets together, we use the union. The last section of this is the decreasing section right here. And this will be decreasing from 1 to 2. Again, starting right at 1 and ending right at 2. So there's an example of going through and listing the where a function will be constant increasing and decreasing. So the next thing to talk about is where we get minima and maxima. So for instance, on this graph, we can see that here we have a minimum. So the point right there, this will be at -2, 1, and what we call the minimum is 1. So the minimum is going to be the minimum height. And we can see that there is a smaller minimum over here. This minimum in this valley is going to be at 3 for x, and then -1 for y. So both of these are going to be minima, and we will call them relative minimum. Now, what does the prefix relative mean in this instance? Well, it just means in a little area around that point, this is the minimum. This minimum is certainly smaller than this other one, but they are both relative minima. So again, in this little area around this point, this is the minimum, and in this little open interval, this is going to be a minimum. So a relative minimum is wherever we see a little valley in the graph. The maximum, in the other sense, this is going to be up here where we have the x value is 0 and the y value is 3. So this is going to be the relative maximum. And again, why do I call it relative? Well, there are points higher than this. So this is certainly not going to be a global maximum. It's not the maximum of the entire graph, but it is the maximum of this little area here. So this is the highest point in this little region. So this is the relative maximum. So again, the relative minimum and the relative maximum is the place where the function value is either going to be smaller than everything else or bigger than everything else, but maybe in only a little area. So here's another example of a function with lots of minima and maxima. This is the sine function, which we won't use very much in this class, but it's good to see. This is a periodic function, meaning that it'll continue this wave-like pattern forever in both directions. And we can see that we have a relative maximum here. So this is at the value pi halves, and the height of the sine function, the height of each one of these crests is going to be 1. So here we have the relative maximum is 1. Whereas a little bit further, at 3 pi over 2, we dip down to -1, and this is going to be the relative minimum. And the nice thing about the sine functions is that this repeats forever. So if we go backwards a little ways, we'll see that we also have another relative maximum at the same height, exactly 2 pi away. And then we'll have another relative minimum exactly 2 pi away. So these are just relative minima and maximum. Then this will also be the subject of the next video, but symmetry is again a rather important part of mathematics. And there are different types of symmetry. So we can have symmetry with respect to the y-axis. Again, the y-axis is going to be this vertical axis here. And when we write symmetry with respect to the y-axis, what we mean is if you were to flip the graph over, flipping it over the y-axis, we will get the same graph. So again, we can see that this over here matches this on the left-hand side after we flip over the y-axis. We can also have symmetry with respect to the x-axis, and it's exactly the same way. So if I highlight the x-axis in red here, if we were to flip the graph over, we will get the same graph. Everything sort of matches. The last one, and maybe the most the least obvious one here, is symmetry with respect to the origin. And the idea here is that if you were to rotate this by 180 degrees, so if you were to get this section down here, the graph will look the same. So this is more rotational symmetry rather than a reflection. This is called symmetry with respect to the origin. And what I'll do is I'll point out a few points in here to help make sure that this is clear. If I pick a point x, y on my graph somewhere, if we have symmetry with respect to the y-axis, this point should appear on this side. And again, the height, because we're flipping across the y-axis, the height doesn't change, but the x value goes from being positive to negative. Whereas if we flip over the x-axis, whatever point we find in the graph, if we flip it across the x-axis, the x value doesn't change. We're not shifting anything from left to right. However, we are flipping from top to bottom, so any positive y value will become a negative y value, and vice versa. Lastly, with the rotational symmetry, this is maybe the least obvious, but what you'll notice is that if we pick a point x, y, and we rotate it all the way around here, not only will we have the negative x value, we're going from the right to the left, but we'll also have a negative y value, we're going from top to bottom. So the way this flips is we will negate both the x and the y values. So again, to summarize, when we have y-axis symmetry, this is flipping about the y-axis. What this means is that if x comma y is in the graph anywhere, then after we flip it, negative x comma y should be there too. So again, we're flipping from left to right. And the way that you would test this is if you had some sort of formula describing your graph, we'd substitute negative x in for y and see if the formula still holds. If it is, both these points are in there and we have y-axis symmetry. Likewise, if we have x-axis, again, this is flipping across the x-axis, so we're changing the height. So if x, y is inside the graph somewhere, x comma negative y should be there too. The x value stays the same, but the y value flips. So again, how do we check if we're given some sort of formula? Well, we substitute negative y for y, and if the formula is still true, we have x-axis symmetry. And then the last one, symmetry about the origin. This is the rotational symmetry. Again, if xy is in the graph somewhere, then negative x, negative y should be in the graph too. And the way we check, substitute both negative x and negative y in for x and y respectively. If the formula is still true, we have symmetry about the origin. And I'll go through more calculational examples in the next video.